previously we talked about the reactions of alkanes, and we saw that alkanes weren't particularly interesting in terms of reactivity because all they really do is combustion. Alkenes are also hydrocarbons, so they will do combustion as well, but because they have a double bond, they will do some more interesting reactions. And you'll see that they're going to do what we call addition reactions, which is kind of a broad umbrella term that encompasses different types of reactivity. With addition reactions, you will see that the name of the reaction gives you a hint as to what's happening in the reaction. So they're all going to be addition reactions. And the first one we'll talk about is hydrogenation. Notice that there is a word, hydrogen, in there. And that's giving you a hint. This is telling you that hydrogen is adding across the carbon-carbon double bond. Keep in mind that in nature, hydrogen is diatomic, so it will come in the form of H2. And it's going to add across the carbon-carbon double bond. So I'll start by drawing up a generic alkene. And I'm just drawing ethene here to keep things kind of simple. And I'm going to draw my hydrogen. So it's a diatomic molecule. It will come in the form of H2. The hydrogens are covalently bonded. So here I have an alkene, which we know is an unsaturated hydrocarbon. The first thing that we're going to do, and I'll color code here just to make this a little easier to see. The first thing we're going to do is break one of these carbon-carbon bonds. We're going to break the hydrogen bond, and we're going to add that across the carbon-carbon double bond. Now, this reaction takes a bit of prompting to get it to happen. It's not going to happen spontaneously. So it does require a catalyst to lower that activation energy barrier. So there are a few metal catalysts that you could see in these reactions. You could see palladium, platinum, nickel, or rhodium. You can pretty much ignore these. They're really there to make the reaction go faster. They're catalysts, so they're not used up throughout the course of the reaction. So they're not going to appear in the product. They're just there to make it go faster. So really, you're going to react your alkene and the hydrogen, and you can pretty much ignore the catalyst. So I am going to draw a carbon-carbon single bond because I broke that second bond. I'm going to keep my hydrogens in place. And I broke the bond between these two hydrogens, so I'm going to take one hydrogen and give it to this carbon, and then I'll take the other hydrogen and give it to this carbon. So I'm going to draw in a hydrogen right here and another hydrogen right here. And that's your hydrogenation reaction. So you took an alkene. Notice you turned it into an alkane when you hydrogenated it. So this turns into an alkane, and this is a saturated hydrocarbon. So you may notice if you're looking at nutrition facts of, let's say, margarine or a variety of fats, you may see a term called partially hydrogenated vegetable oil. This is the exact reaction that's happening in that process. They're using oils that have a variety of alkenes throughout the chain of the fatty acid, and they use hydrogen to hydrogenate it. Now, if it's partial hydrogenation, it's saying that not all of the alkenes are hydrogenated, but some of them are. So you end up with a mixture of alkenes and alkanes in the product. We'll talk about one more addition reaction of alkenes, and that is hydration. And here the name is also giving you a hint as to what's happening. So if you are hydrating yourself, it's saying that you're drinking water. So in this case, water adds across the carbon-carbon double bond. So I'll start by drawing my ethene. And here we're using water. I'm going to draw it as HOH just so I can see very clearly which bond is being broken. This is going to require a catalyst as well. It requires a strong acid. So you could see this as a generic H3O+, or you could see it depicted as a strong acid. So for example, it could be sulfuric acid that's serving as a catalyst. Just like any catalyst, you're going to leave these alone. You're not going to draw them in the product. They're just there to make the reaction go faster. So I'm going to start by breaking one of these carbon-carbon bonds. Then we're going to break a bond between the hydrogen and the oxygen. And then I'm going to take one carbon, give it a hydrogen, and to the other carbon, I will give the OH. And I'll color code that here as well. Okay, so this carbon gets a hydrogen, this carbon gets an OH. Here we started with an alkene, and we end up with an alcohol. We'll talk more about alcohols in subsequent videos, but whenever you have an alkyl group that is attached to an OH, that is an alcohol. The thing to keep in mind is that we started with a symmetric alkene. Notice that both carbons had 2 hydrogens on them. There were no other groups. And you could have a scenario where you have an asymmetric alkene where one of the carbons has a substituent and the other one maybe doesn't. So let's take a look at that example. Okay, now notice this carbon has 2 hydrogens. This one has a hydrogen and a methyl group. So now we have to decide, well, if I break that hydrogen-oxygen bond, where does the hydrogen go and where does the oxygen go? Now I have to make a decision on where to put each of these groups. And the rule that we're going to use is that if the alkene is asymmetric, you will give the hydrogen to the carbon that already has more hydrogens. So if I focus on this alkene, notice this carbon has 2 hydrogens on it, and this carbon only has 1 hydrogen. So I'm going to take this hydrogen and I'm going to give it to this carbon that already has more of them. Other than that, everything else will be the same. So it'll be catalyzed by a strong acid. I'm going to start by breaking one of the bonds between carbon and the other carbon. And now on the carbon that already contains more hydrogens, I'm going to put a hydrogen, and the OH group will go on the other carbon. And that's basically it. That's how you're going to do your addition reactions of alkenes.